Okay people, so here we are back again, continuing our work with probability. Today we're focusing on discrete random variables and we'll talk about a definition of those just in a minute. As always, if you spot any mistakes, please make sure you let me know. If there's anything you don't understand, please keep a note of it and ask me next time we have class. Okay, let's get started. So first of all, we need to define the difference between a discrete variable and a continuous variable. Now this is something that you should have heard of before in other years of your schooling. If you do further maths, you might have discussed it earlier this year. So have a think. If you already know what this is, excellent. Otherwise, pause the video, have a think, and then let's continue. So our discrete variables are variables that can only take distinct values and nothing in between. This doesn't mean necessarily that they have to be only whole number values, just that there are only certain values they can have. Generally, for discrete variables, we work these out by counting. Okay, so examples are things like the number of females within a maths methods class, or the number of goals that a particular team got in a sporting match. Another example is shoe size. So this is a good example where we can have half values, because you could have shoe size 7.5, that's fine, but you wouldn't be able to go into the shoe store and ask for a size 7.25 shoe. I think if you did that, they'd look at you like you were a bit crazy. So this is still discrete because shoe size can only take certain values. Some stores might have half sizes, but you're never going to find these quarter sizes here. On the other hand, we also have continuous variables. So continuous variables can take any value within a certain domain. To get these, we tend to measure to find our continuous variables. So when we're measuring things, we've got things like weights of packets of cheese, so they would come in a variety of different weights, and we can have decimal answers, fractional answers, any possibility. If we think of other types of variables that we can measure, other possibilities when we're measuring things like heights, so heights of trees, heights of people, and again, that can have any number, any decimal or fractional number. We could talk about times, the time taken for a cake to cook, the time taken for you to get home. We could talk about areas, the area of a block of land, and a whole lot more as well. Essentially anything that we measure is continuous. When we have to count it, or when it only takes whole number values, we've got discrete variables. For today, we're just going to be concentrating on discrete. So this is our focus of what we're looking at right now. We are going to get back to continuous later on this topic. Okay. When we have a discrete probability distribution, so remember, discrete means only certain values are allowed, not all possible ones, only certain values. And our probability distribution, we've got a way of representing this. It is a listing of all possible values of a particular random variable that we're considering and their associate probabilities. So as a quick example of a probability distribution, if I was to roll a fair die, we could let x equal the number of dots shown when we roll a die. Okay? Because that's what happens when we roll a dice, it generally has the number of dots on it. In our probability distribution, x is what we're trying to find out, and our options could be there's a 1, 2, 3, 4, 5 or 6. We then work out the probability that our capital X, which represents this bit here, the number of dots shown, is equal to our little x, which are these values along here. Now in this case, assuming it's a fair die, not biased, therefore there's an equally likely chance of landing on each of these. There is a 1 in 6 chance that we would see 1 dot, a 1 in 6 chance we'd see 2 dots, And again, you can see our pattern here. There is an equal chance for all of them. So this is an example of a probability distribution. We have some properties. Oh, sorry, I've written over this here, but it shouldn't bother you too much. Some properties of a probability distribution function. First of all, we're saying that each of the probabilities here must be between 0 and 1. And that makes sense for our example here. All of our probabilities were 1/6, so they were all between 0 and 1, no bigger than 1. And that's the case for all probabilities, like we know. Second, we know for a probability distribution or a probability function, the sum, remember this symbol here is a Greek letter meaning sum, the sum of all probabilities equal 1. And if I was to add all of these together, 1/6 plus 1/6 plus 1/6 plus, we would end up with 1. What that means is it's certain that one of these options in our sample space, either 1, 2, 3, 4, 5, 6, will be shown when this event occurs. Finally, we say that the probability of achieving between A and B, so in our example earlier we could say the probability of getting a number between 2 where x is less than or equal to 2 to 4. The way we do that is by summing all points between x equals A and x equals B. So in this case we add together all values of x between 2 and 4 and including 2 and 4. So I'd add this 1, 2, 3, 4. Adding those together we would get 4/6. Oh, whoops, I've added too many, haven't I? We shouldn't be including this one here. So adding the other ones together, let's try again. Sorry about that, everybody. So we're adding together the probability here for 2, 3, 4. Those are all values of x that are between 2 and 4. 1/6 plus 1/6 plus 1/6 gives us 3/6 or a half. Okay, let's look at our first example. So in this case, what we're looking at is x representing a number of tails obtained in 3 tosses of a coin, and we need to construct a probability distribution table and a graph to represent it. Now, if you're not sure about the different options here, we can always use a tree diagram, so let's have a look at that. If we throw our coin, we can get a heads or a tails. First throw, second throw, heads or tails, second throw, heads or tails, and then our third throw, once again, we can get a heads or tails. So by doing this, by using our tree diagram, this allows us to come up with our sample space. Okay, so our sample space are all of the options we're going to get. So we could have heads, 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 tails. So I'm following the branches along. Heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails. Okay, and we've got all of our options there. Now, if we are thinking about what's actually happening in this case, x represents the number of tails. So if we look at what's happening for x here, our number of tails, with each of our options in the sample space, with our first option, heads, 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 there was 0 tails. The second option, heads, heads, tails, there was 1 tails. Heads, tails, heads is 1 tails. Heads, tails, tails, we've got 2. Tails, heads, heads, 1 tails again, 2, 2, and 3. So here then, these numbers we can see here, these are the ones that form our sample space for x. Our probability distribution for x, the different values that x can have, represents the number of tails we could get, so these are the different variables, the different values that x can have. So we then go ahead and construct our probability distribution table. is what we're looking for here. Little x represents our different options, and we can have either 0, 1, 2, or 3 tails. Here we write the probability that capital X, which is our number of tails, equals lowercase x, which are the options 0, 1, 2, 3. So to fill in to start with, we ask the probability that x, which is our number of tails, equals 0. We have got 1 out of 8 options. The probability that x, the number of tails, equals 1, we've got 3 options out of 8. Probability x equals 2, we've got 3 out of 8. Probability x equals 3, we've got 1 out of 8. So when we say, just to clarify, we're getting these numbers from this here. We're seeing how many of these options fit each of those circumstances. Finally, we need to draw our graph. When we draw our graph for our probability distribution, on the y-axis, and if you have a ruler that would be better, we put the probabilities, and on the x-axis we put our different values of x. In this case, that represents the number of tails. Now we don't actually have to start 0 at the origin in this case, because what we're going to do is draw some lines to represent our graph here. Our maximum probability could be 1, so we can put some other scales in, and again, if you have a ruler, that would be helpful. I will point out that it's actually not overly common to need to draw one of these in an exam. Okay, so for 0, a x value of 0, we have a probability of 1 over 8, so I draw a line up. I draw a line to 1 over 8. Of 1 is 3 over 8, so I'm going to come up to 3 over 8, and I draw a straight vertical line. 2 is 3 over 8, straight vertical line, and x being 3 is 1 over 8. And this is our graphical distribution of this particular function. Okay, so with our next example here, we've got a slightly more complicated distribution to form. Once again, I think that drawing a tree diagram is going to be really useful to get our probability distribution for y, which is our number of white socks. So if we draw our probability our tree diagram, our options, we can put our hand into the drawer and we can either find a white sock or we can get a black sock. There are 12 socks in total, so in 12 is our denominator, that's the number of possible outcomes. Number of favourable outcomes, there are 7 white ones and there are 5 black ones. Then we continue on to the next part here. Once we've done that, we can again, in our second drawer, get a white sock or a white or a black sock. Now if we've already taken one out, okay, because they're drawn without replacement, this means that our denominator, our number of possible outcomes, will change. So we've already taken one sock out. That means there are now 11 left in the box. So our denominator in each case will be 11. Let's consider the first option here. If a white sock was drawn to start with, then that means I will now only have 6 white socks left. So I'll only have 6 white socks left in the box. If a white sock was drawn to start with, that means I still have 5 black socks. Notice that the two probabilities on these two branches should still equal 1. Our other option, if we draw black socks to start with, that means that I now only have 4 black socks left, so I've only got 4, but I've still got 7 white socks. Now from this we can get our sample space, which will show we can get 2 white socks, a white then a black, or we can get a black then a white, or we can get a black and then a black. if we're looking at our variables for y here, so our y values, which is our number of white socks, we can either get 2 here, 2 white socks. White then black is 1 white sock, black then white is 1 white sock, black and black means I've got 0 white socks. Now we can construct our probability distribution. So we draw our table here. We've got y and probability that capital Y, our number of white socks, equals lowercase y, our options. Our options are 0, 1 or 2. Now actually filling it in the table in this case is a little bit trickier. So if we're wanting 0 white socks, that means we want to get a black sock and then a black sock. Remember, when we say and, it implies, or another way to think about this is, when we're going along the denominator, we are multiplying. No, sorry, I can't write down there. Let me come up here. So if we want a black sock and then a black sock, what we do is we say 5 over 12 times 4 over 11. They're independent events, and we multiply these. Now, we can work this out in your calculator, but you do need to know how to do fractions, how to work with fractions as well, because sometimes it comes up in tech-free. But it does simplify to give us 5 over 13. If we want 1 white sock, that means we can have white then black, or we could have black then white. So white then black means we multiply along the branches, 7 over 12 times 5 over 11. Or, remember when we say or, we add. We could have a black sock, then a white sock. 5 over 12 times 7 over 11. Again, we can work this out by hand or in our calculator, and we get a value of 35 over 66. Our final option for 2 white socks, that means we've got white, white. We would have 7 over 12 times 6 over 11, which we work out when it simplifies gives us 7 over 22. So this is our answer to part A. This is our probability distribution. Next, we can use this to answer some of the questions. So part B, determine the probability that 1 or more white socks are obtained. First, we write this as a probability. Probability, Y represents white socks. 1 or more means Y must be greater than or equal to 1. Greater than or equal to 1 means we've got this option here and this option here. Y can equal 1 or 2. 1 or 2, remember when we say the word or, it means that we have to add the probabilities. Probability of 1 sock, 1 white sock, is 35 over 66, or we write a plus. 2 white socks, we work out these ones here. And we can put this in our calculator, or we can work it out ourselves to get our answer. Remember, always have a look and notice my probability is less than 1, which is what we're wanting. Finally, our last part, part C, we want to find the probability Y equals 2 given Y is greater than or equal to 1. So what this actually means is we want to work out the probability that we get 2 white socks, knowing or given that we get at least 1 white sock. So our formula, which remember is not in our formula sheet, is we see where the 2 probabilities intersect divided by the second probability. Now if we are thinking about this, we want it to be where does 2 and greater than 1, greater than or equal to 1 intersect? Greater than or equal to 1 means we'd be looking at this option onwards. Y equals 2 means we're just looking at this option here. So together, where do they intersect? Just where Y equals 2. And we divide by probability Y is greater than or equal to 1. Now we can substitute in probability Y equals 2 from our table is 7 over 22, and we need to divide by probability y is greater than or equal to 1, we work this out in part B, 28 over 33, which when we simplify again by hand or in the calculator, we get our answer of 3 over 8. Our final example for today. So we're looking at a discrete probability distribution. Because they tell us it's a probability distribution, that means we know that the sum of the probabilities must equal 1. So to find the value of A, we know that if I was to add all of the probabilities together, it must equal 1. And we can work this out, and we get an answer that A is equal to 0.03. So we know we have 0.03 here. For part B, it's conditional probability, and remember it happens where they intersect. So our formula is, where they intersect divided by the second part, probability x greater than 1. Now if we think of where these intersect, our options are 1, 2, 3, 4. X less than 4, that means I'm not including 4 and I'm heading in this direction. X greater than 1, I'm not including 1 and in this direction. For what values are they both true? 2 and 3. So what I do here is I add together those options. Another way of saying this, by the way, is that x must be bigger than 1 and less than 4. So if we have a look here for our options that are bigger than 1 but less than 4, we just have the option 2 and 3. So I add together those probabilities because I could have 2 or 3. And we divide this by the probability x is greater than 1. So x being greater than 1 means I could have the options 2, 3 or 4. We add together our probabilities here, 0.32 plus 0.51 plus 0.03. Working these out, adding them together, we get 0.83 divided by 0.86. Now it is very important that we don't leave our answer like this. Having decimals within fractions are not at all nice. We need to convert this to a fraction. If I was to multiply both the numerator and the denominator by 100, that means I move my decimal place 2 spots to the right, and I end up with 83 over 86. Remember, as always, you must simplify the fractions if you can. In this case, this is fully simplified, so this is our final answer. And so this is how we work with probability distributions for discrete random variables. If there's anything you don't understand, please let me know. Until next time, goodbye.